Well, thanks very much for coming and having another hammering for the morning. I've taken very bombastic title, have statistician made any real impact on image analysis? I think some of you perhaps know the answer, but I don't. And we will just try to go through the journey and see from the experience whether we have learned some lesson in this area. The subject from a statistical point of view, it started about 30 years ago, 3 decades or so. And I will give you some historical background to it. I have got a mission statement from Leeds Annual Statistical Research Workshop, or LASER in short, and LASER will keep on coming into it. And the mission statement, now this LASER is going on for last about 30 years now. It's an annual workshop, and quite many were dedicated to image analysis and interaction with other discipline with image analysis. So there is a lot of emphasis on bringing two community together, statisticians, mainstream, and the people who do the real collection of data, as well as they know inside and outside of these images. So this mission statement, which has just been produced, statistics without science is incomplete, science without statistics is imperfect. And I think that's the thought which is going through all of our LASER workshop, that what we want to do is to develop a community in some emerging new area which will excite statisticians as well as which will excite the scientist. And I'll give you some flavor slowly, gradually. So contents, first is slight introduction, which has been asked by the chairman to give what are images or what are image analysis. Then there is a brief history, so looking into past. Then a success story where there has been something nice for all of us, statisticians and image analysts. Especially, I will focus on one area. There are many, many areas, shape and images, and one particular thing, point model distribution. Some of you wouldn't know. You will take it to be some gamma distribution or something else, but it is not. It's quite contrary. Then the other topic would be something which should happen in near future. So it is a timeline. Topics waiting for deeper interdisciplinary interactions. And there are two topics where statisticians have done something, computer scientists another, but the interaction is not as much as one would have liked to have seen. Topic is still evolving. The field is not yet complete. I think the evolution is a slow process. In everything, there is an organic growth. And organic growth depends upon fertilizers and the land and soil and all that kind of thing. And then some concluding remarks, some form of soul searching. So that's the overview of the talk. And so I will start with something which we are proud of, what we did in Leeds. So there will be some bias, I'm so sorry to say, from what has happened in Leeds, but there will be beyond it as well. So we had problem about 1999. This is someone who had an accident. I think this is a trauma. It's a true one. And the CT scan was taken, and there was a company which came to us to see they want to make this prosthesis piece, and would we help them, whether it will fit in. If it doesn't fit in, I think it can be terrible, I think, for the poor patient. And it has to be within given time limit. We couldn't just sit there and produce some form of fancy models and algorithms. So I think that's so this was from 3D prosthesis, from CT scan, how to produce. And I will come back as we go along that what happened and how happened and what were the new challenges from a statistical point of view. Now, quick definitions. So like every field, the definitions are plenty. And I think the more important is that computer vision, from the one definition, is science and technology of machine that see like humans. So I think mimicking human being is one of the aim of image analysis, among other things. And I will just switch between the two image analysis synonyms. I will take at computer vision. So I think if I'm shifting, it is the same meaning. Then this the definition which I like from one of the very popular textbook in computer vision by Forsyth and Pons, 2003. So we see computer vision as an enterprise, and I like this word that uses statistical methods to disentangle blah, blah, blah. I thought that was something which I was looking for. I could have constructed myself, but it would have been rather cheating. So, but this is one of the most popular textbook just now in computer vision, and it is nice to see that statistics as a discipline has been recognized. So this is another view, a flower petal view of the subject, that they are computer vision, machine vision, image processing, image analysis. But this is mostly academics, that how academic part, and you will see mathematics, statistics, geometry, optimization, and many other artificial intelligence, machine learning, all these areas we now know. If you would have asked 20 years ago, some of things like we would not have heard of. So things, there are plenty, especially this optics, physics, how the images are coming, from where they are coming, what is the background. Could you hear me now? I can ask, having said so many things. Is it back? Am I okay? Oh, good, thank you. So now this famous sentence, digital images are everywhere. Now I had a camera just now, digital. I took one, and I'm very proud that I took with David Finney, actually one. Anyway, so if you look at some of the area, which is biomedical imaging, which is where we were once, remote sensing, automatic surveillance, technical diagnostic, and you can add face recognition, fingerprints. We dabble with quite many of these things, and not that we reached big heights, but at least we were catalyst, if nothing else, in the field. So this is taken from the famous book, Image Analysis, one of the first book, I think, is it not, Chris? For statisticians in a way. So just two jargon will be very few, only two jargon. One is low-level image analysis, which is an image with coarse resolution, and you want to enhance. That's one thing which will come. The second is high-level image analysis. This is a great simplification. I think it's those who are in image analysis field will be horrified, but please, I do apologize. So high-level image analysis, this is H, and how to, when you got all these numbers, gray level, how to get H, and when in colors, what happens. So these are the very elementary type of image analysis, low level, high level, then there is a middle, and all those kind of things goes on. So 3 decades, now we go to slight bit of background history. So 1980 was emergence of statistical image analysis. I'm sure someone will say this is not true. But at that time, there were no cheap images. I think we went through a period in our Center of Medical Imaging Research to find images from doctors. It wasn't easy, MRIs and all that. So, but now digital color images are easy. I think, do you agree with this? Are they easy now, images? I think everyone is having now. They have got videos, they have got all even webcam and whatnot. No fast computers at that time. Now laptop itself are powerful, and someone are already working now, just now here. No web, no electronic publishing, no Wikipedia. All this, the background of, if you go back 3 decades ago, it wasn't as good of data as what it is today. I think things have changed. Now again, key points. Low level, there are a lot of smoothing and classifications. That's the work which statisticians and others have done. High level objects, prior knowledge used in image understanding. I think again, statisticians in Bayesian paradigm. Modality, this is the third key point, that how to incorporate type of sensor, type of cameras, whether it is a remote sensing or whether it's CT or it is MRI. 1990 plus computer scientists came with full force and left statisticians hanging behind, as this is my feeling. Use of heuristic solutions. I think that became the word. Heuristic, concept of heuristic knowledge may be both empirical and very vague in nature. So heuristic solutions, what they are? They are fast but suboptimal solution, but these may be adequate in practice, so who cares? As long as it works, I think that's what the engineering approach is, and that's what has won. So statisticians do improvement maybe about 5% or 10%. I think this is, I'm talking of few part of image analysis, but they could do 80-90% work. So brief history now, going back to 1950, 1970, MIT did quite a lot of Maryland, Adriel Rosenfeld, and then late King Sun Fu. So Adriel Rosenfeld, he came to Leisure, one of the workshop before he's died as well. Ulf Granander, he came to Leisure, pattern analysis. Now he is the one of, I think I would regard as the guru of, from a statistical point of view, of image analysis. So he has now, he started in 1970, one of the important pioneering paper. Then there are books, but it is Gieman and Gieman paper. Most of you are familiar, I think. Are you familiar? At least you have heard of it. I think that started quite a lot of a race, MCMC and various other phenomena in PAMI. So now MCMC is the top 10 influential algorithm in science of 20th century. So this MCMC, what word was not even known, now it has gone quite high up. A new book of Granander group is with Michael Miller, 2007. Worth looking at it. I think it's a real challenge. And I will just sketch a few things in the time frame I have got. Then brief history too. I think statisticians were more influenced, at least I was influenced, Julian Bisag was influenced, and many others because of Paul Switzer from Stanford. In 1980, I heard him in Geological Congress, and then he was doing something for remote sensing data. And I thought that looks good, actually. It's some data on lattice, and let us try our hand in what he has made. So this was large pixel size. They were mixed pixel, but the ground truth was available, and which is not always possible. So that's, and this is Landsat 2 in action of that time. I think things have moved more wavelengths, and this is the data, very rough, mixed pixel size, sorry, I think I'm going, 1.5 acres. It's a very large now. The resolutions have increased, so the technology has increased. At that time, we worried so much about mixed pixel, fuzzy classification. Now I don't think there is a great problem. Now some landmarks, as I just said, that 1980, Paul Switzer, then Julian Bisag in 83 was discussant. I wrote a paper, and I just attended the previous session on FDR. And in the beginning, when you have got something new, I think it goes through a high editorial thing. I won't go into the history of it, but it went around in so many different journals until I decided had enough and took home stats. Gieman and Gieman paper, I've already talked. Then first ever International Statistical Image Analysis Conference was in Leeds, all inspired by, I must say, by Paul Switzer. I think he's a good friend of ours. Then Edinburgh, it was the EPSRC. It was a very big, exciting meeting where a lot of brainstorming took place, and I think 1986 paper of Julian, partly the seed were shown here actually, and so on and so forth. The one other thing was edited 2 volumes. I studied in images. Some of them were pioneering papers, and some were the new papers, and then various later workshop on images. 25th anniversary we had in 2006. So I will move. Now this is now you try to find who is who. So, so it needs image analysis enhancement. I think it's a blurred image, but it's 25 years ago. There are few things you will recognize. I will leave it at the end. I can come back, but won't spend time. Then RSS did a great service, I think, which is they had many discussion paper, one after another, a set of discussion paper, including of Granander and Bizag, which was in a way quite pioneering. I think UK had a lead in this in comparisons to other continents, I think. So now, having given this bombastic title, I started wondering, having given well in advance, how to measure impact of statistics on image analysis. Now, I've seen in other talks, people go for citation. They look at Google it, and try to see how many citations are there. And I don't think, personally, that's a good way for a new subject to assess. So I went for which statistical books or statistical ideas came and filtered into image analysis into computer vision books. And I think that's where the real grassroots is not Google or anything. Grassroots is where it's being taught and where they are learning MC, for example, not in statistical discipline, but elsewhere. So which statistical group have sustained the collaboration? Because we all started very high-level collaborations in 80s, and some have disappeared, I think, had an early death. Some are still continuing, limping, but continuing. Then which are the high-level? I won't go for citations and conferences myself on this, but which industry, healthcare, MOD, etc., have benefited? Because some of the work is unclassified, so people have done work, statisticians, but it can't be measured. So impact would be which topics have filtered into textbook for computer scientist or image analyst. So this is one book. It's not to as a sale idea, but so we have statistical shape analysis. That's the one area which I said I'll be talking about because I'm sure of where the subject has gone. So shape is defined. I think I will go through very quickly that it should be some form of invariance. Locations, if I move, my shape remains same. If you take my picture from different view, scale it remains same. If I move around, then I remain the same Mardia. And so that's, but it is different type of statistics, different manifold than the common manifold, linear manifold. And then another size and shape where scale is not to be filtered out. It's important, my face versus a baby face. I think that's where, anyway, I will go through, and the one which I said point distribution model of Coutts, and very quickly, they are a group, Manchester group, and they fortunately kept on coming to laser workshop. So we statisticians were hanging on and trying out all distribution theory while they tried to see how to make it practical, and presented a lot of papers. So it is a very simple idea. You register it by removing those effects. When you've got landmarks like on the nose and so on, they are all landmarks based. Obtain the shape mean, obtain the usual kind of a sample covariance because they have already filtered out, and then you go through usual principal component analysis. But the twist is here, that when you have got mean, then how to see the variation in shape, and which is much more perceptible than ordinary PCA. So if you see, like this is a very good example which is taken at what I edited in 1994, that this finger, you can see relative motion of thumb and fingers in this. That's the first principal component of shape. Then this is the second, where the thumb is moving out, and this is the middle finger versus the motion more middle finger. So spreading of fingers in number one, thumb dynamics in number two, But this seems so simple, but they have now taken it quite further, used it in all kind of important applications and advanced to, and this has been one of the hit. So if you look at textbooks, you will find, did I put, I think, let me see. Yeah, so that was the important point. So this is the third edition of this book, 2008, and it contains chapters and chapters on this particular techniques. And so it is filtered through the shape part into the community of image analysis. Many extensions you can think of. I won't go through it, but the only I will comment, this work has a lot of heuristic, but it does the job and become a standard tool in image analysis. I think that's the one of the, now I go into the second topic, which is still waiting for interaction, image warping. And I think I couldn't resist with RSS, with R.A. Fisher, E.S. Pearson, they are merged. Now merging is so common, but if you talk in 1993, there were no software, and it was one of the unique things. And I think I could recognize this face. Some of you might know as well, who is the merge. So the one which we did in warping with Chris Glassby, that there was a problem of Haddock and Whiting, how to discriminate with landmarks. It wasn't easy. We produced a penalized likelihood approach. Sorry, I think I'll just jumping. Then there are other approaches. Granander School, late Keith Worsley, functional MRI, computers PDM, what I passed on. So there are quite many different approaches, but there is no synthesis yet. So this is something remains to be seen. Then another one which needs filtering is occlusion. I think you see now these kind of pictures quite often and try to see if there is any suspicious character in it. I think maybe a bit below the umbrella, but who knows. Anyway, the one which we had a project with Silso, and it was grading mushroom, and it was a small image, and we used Bedley van Lieshout's Markovian object process. I won't go into detail. And the results were here when you use deformation and you do without deformation, robotic mushroom recognition through Markovian object process. The talk by Dr. van der Heijden will be giving more on robotics ideas, what recent. But this is still, the object processes, I think, as far as I know, is not filtered through. Now, the subject which is evolving, I think, although we know face recognition, quite a lot of things going on. And this was live with one of our industry which we are working on, face recognition before the September 11th incidents. So this goes again 1999, that they were given this too, and we had a method how to, from the set, this was just a few were given at the last minute, and it went into the live tomorrow's world or something like that. And to recognize out of 1,000 this two. So we had this projective shape space, and we did quite a lot of work, but still there are two different views, computer scientists and statisticians. The statistician work is still not complete. It needs a lot of further work. Anyway, now we come to this missing piece. I think that's the one which is what I said is still on surface, subject evolving, surface matching and prosthesis, CT image. So how it was done, and it was very cruel in some sense. So we took cadavers. I think we didn't take, fortunately, anatomist. Okay. They produced, sorry, how many minutes did you say? Can't see it. 5. Okay, good, thanks. So produce CT scan of area, capture the geometry, make the prosthesis piece, and they are how to go from stage 1 to stage 3. There will be talk by the next speaker, Dr. Elke Thonnes, more on surface. So it was very gruesome experience, especially I being Jain, that they took cadaver, chopped their head off, took CT scan, took the skull and then compared the model which came from CT scan and see what was the difference, how reliable were these stereolithographic model, which is this is the model. And after all great statistics, what it turned out to be that it was just the size, uniform size difference. There was a constant ratio. I wish there was a more to it, but it turned out to be it didn't need very deep statistics. Actually, it is some part of scale, what I said is scale and shape theory. So topic not covered because of the time. Green, who is here already, he has done this reversible jump, is a now household word. They are highly structured stochastic system. Again, there is a image analysis view on Bayesian view on image analysis. Low-level models I haven't discussed, mid-level data models for, and so on and so forth on quite a lot of important work on statistical learning, neural nets. I think the field is really bubbling. Algorithms, EM, we have already heard, but the news, I've been talking to Microsoft, some people gave some secret, that 2010, they are using these kind of statistical technique for background removal. I was very pleased, actually. And Microsoft in autocollage software also, they are using the models, statistical model. Then all these, but the last one, I am more now into biomarkers from electrophoretic protein gel images, more biomarkers, be more on protein-related stuff because there seems to be quite a lot new work to be done, I think. Conclusion. So heuristic are acceptable like an MC, ignore convergence, detailed balance, topmost priority for computer scientists, simple, problem solving, fast method, software. Statisticians go slightly in different way. I think we all know how we work. So I think there is no point in my. So the subject slightly hampered because of our priorities, which are, I'm not going to say whether right or wrong. So they are different priority. And when industries, when they think of any consultation on images, they think of computer scientists, not of statisticians. I think it takes quite, unless you are doing it. So lessons, what are the lessons from this? To follow the role model of Granander School, who are continuously, all three people, statisticians, mathematicians, image analysts, moving with time and technology. You have to move with technology. There are more resolutions, there are different statistics. Okay, good, thank you. To create themes in regular annual workshop, laser is one, but there are many others. To find such group for long-term collaboration, we got from Manchester. Then center like BIOS, I think I could have removed that actually. So one thing which with Wally Jilks is about what I call holistic statistics. Are we searching for any new names? I think that was the question was asked. And what it says is some form of paradigm shift, and this is the elephant and 6 blind men, 1 blind man is missing. And that you have to take truth as whole truth, is a holistic approach, not that I am interested in inference. I think it's the wrong place there, Bayesian especially, algorithms, models, learning, image science, and all these words are for statistics as well as for image analysis. And I should end here. I think he's going to smack me. I think.
First of all, I would like to thank the organizers and Chris Glasby for the invitation to speak here. And I thank Professor Mardia for giving such a comprehensive overview over the area. And what we'll do now is look at one specific problem within the area. It's a fairly recent project of mine where I'm looking at high-resolution CT scans of lung patients. And as is common in image analysis, I'm interacting with various people on that project. There is David Parr, who is a respiratory consultant at the Coventry and Warwickshire University Hospital, Abir Balarao, who is a computer scientist in the imaging group at Warwick, And Michael Karemza and Jonathan Strickle are two MSc students who worked with me on various problems. Kanti, what happened to me? The pointer. Oh yeah, here we go. Right. Okay, so high resolution computed tomography, I'll move a little bit down here so I can actually see my own slide, is currently the most accurate non-invasive method to assess lung pathologies, and it's used to diagnose but also assess the extent of various lung diseases. Two such lung diseases, which I will talk a little bit more about, are pulmonary fibrosis and emphysema. So at the bottom, you see a horizontal slice from a 3D HRCT scan, and resolution isn't great on the actual projection, but normal lung tissue would usually display as dark gray. Other tissues, such as blood vessels or scarred lung tissue, is displayed as white or light gray, and air trapped within the lung appears as black voxels. Okay. Now, emphysema, well, we all know that the function of the lung is to oxygenate blood, and the way that works is that you've got little air sacs within the lung, which are called alveoli, and they stretch and contract to allow that gas exchange. And when you have emphysema, then the lung tissue loses elasticity, which means those alveoli can't function properly. And so what happens is that air becomes trapped in the lung. In terms of healthcare costs, emphysema is quoted as one of the top 5 Western world diseases. A major cause for emphysema is smoking. There's no cure for this disease. There are various treatments that can alleviate symptoms, but in severe stage emphysema, really the only option you have is surgical reduction of the lung, which obviously is quite severe intervention. In clinical assessment, besides actually having an expert radiologist looking at the HRCT scan, if you want to do automatic assessment, what people do is they compute what is called the emphysema index. Now, as I said, trapped air within the lung is displayed as very dark voxels. So what the emphysema index is, it's just computing the ratio between the number of voxels with a gray level that's below a certain threshold divided by the number of voxels with a gray level that's above a certain threshold. And so that's really very crude measurements they're doing. And not surprisingly, it fails in various scenarios. So there are two example scenarios are that when you've got mild stage emphysema, often the abnormal regions are quite small compared to the healthy regions within the lung, and they're dispersed throughout the lung. The other scenario is when you have emphysema co-occurring with fibrosis. Okay, so here's an example of such a case. Fibrosis is essentially scarring of the lung tissue. The tissue thickens, and that becomes visible as lighter gray areas within your HRCT scan. And in severe stage fibrosis, what you see is a network of the scarred tissue developing, which is commonly called the honeycomb. And as you can see here, that's quite an appropriate name of describing it. But at the same time, what you see, or I hope you can see, is that in some of the cells within your honeycomb, you have dark patches, and this is traction emphysema that co-occurs with fibrosis. And so this is another scenario where the emphysema index may fail. To assess fibrosis, what people do is essentially they look at the range of attenuation values and then produce, again, one numerical quantity, which is often the lung mean density or a percentile of the attenuation values. Okay, so quite crude assessment methods that are current clinical practice. Now, when I initially was presented with the problems, I immediately thought, well, you really want to have some topological measures to describe the different pathologies in the lung. And there's a very nice and elegant approach to describe shape and topology, which are the so-called Minkovsky functionals from integral geometry. So there are various names for these Minkovsky functionals. They're also known as square mass integrals or as intrinsic volumes, but essentially they're all the same. And they've been used very successfully in material sciences to describe and distinguish two-phase media. So that could be, for example, porous media, foams are commonly examined with these Minkovsky functionals. What is also nice about these is that for a variety of stochastic geometry models, such as the Boolean models or various derivatives of Gaussian random fields, you can analytically compute those Minkovsky functionals. And so that means that you can actually fit stochastic geometry models to your observed data. Now I know why Kanti was over on this side, because you can actually see the clock if you're over here. Okay, so what are Minkovsky functionals? There are various ways of defining them. One is the Steiner formula, which looks at a compact convex set which is dilated by a sphere of radius r. And now if you compute the volume of that dilated set, you find that you can express it as a polynomial in the radius r of the sphere. And the coefficients of that polynomial are proportional to the Minkowski functionals. Now, if you actually look in R3 what the actual coefficients are, you realize that they are quite familiar geometrical properties. So in 3 dimensions, the volume of the dilated set can be written as a polynomial whose coefficients are the volume of the original set, the surface area of the original set, the mean breadth of the original set. So mean breadth is essentially proportional to the integral of mean curvature, and the Euler-Poincaré characteristic, which is a topological measure. It's a connectivity characteristic. In 3 dimensions, you usually have this nice expression that is the number of connected components plus the number of cavities minus the number of tunnels. Okay? And there are similar expressions for 2D. In 2D, you would get the area, the boundary length, and again, the Euler-Poincaré characteristic for 2D. Okay? Now, these functionals have really nice mathematical properties. They are motion invariant, so they're invariant to translations and rotations. They're continuous in a certain sense, and they're C-additive, which essentially means the union, the Minkowski functional of the union of 2 sets is equal to the sum of the individual Minkowski functionals minus the Minkowski functionals of the intersection. Okay, so that makes the computation of these Minkowski functionals very straightforward and convenient. And also you can use the additivity to extend the definition of Minkowski functionals from compact convex sets to unions of compact convex sets, and therefore the convex ring. Okay, but what is really striking is that these Minkowski functionals satisfy a certain completeness property, which essentially means that any motion invariant continuous and additive functional on the convex ring can be described as a linear combination of Minkowski functionals. Okay, so there's a really nice, elegant, sophisticated mathematical theory behind Minkowski functionals. Now let's look at Minkowski functionals for images. Okay, so we're considering binary images. Now each voxel in a binary image can be interpreted as compact convex set. And the union of black voxels then is a polyconvex set, so we can compute the Minkowski functional of that polyconvex set. To do that, what we do is we consider each voxel, black voxel, as a disjoint union of the interior of that voxel, of the open faces, open edges, and vertices. And the idea, obviously, of choosing a disjoint union is to be able to use that additivity that I mentioned earlier. Additionally, you can exploit a very simple relationship between the Minkowski functional of a set and its interior. And putting these bits together, you then get very simple expressions to compute the four Minkowski functionals, okay? Which essentially just are based on counting the number of cuboids of black voxels, the number of faces, the number of edges, and number of vertices. The only thing that you need to make sure is that you are not double counting any faces, vertices, or edges that are shared by neighboring black voxels. Okay? So this is very easy to implement, quite fast to compute, and to a certain extent is sufficient if you just want to describe binary images. Okay? It is more complicated if you actually want to go from a description of your binary image to inferring the properties of the set that you imaged. Okay? And when did I start?
About 17 minutes past.
Okay, all right.
So finishing about 18 minutes till.
Okay, all right. So I'll just really scan over this quite quickly. So essentially the problem you're having is you've got a continuous set, you image it, and when you image it, you discretize your continuous set, even if the imaging process doesn't suffer from any noise. And what the previous algorithm essentially does is it approximates that continuous object by a union of cuboids. Okay? And that obviously will then mean that when you estimate the Minkowski functionals from that union of cuboid, you incur an error in your estimation. You incur a bias. Now the problem is that naturally when you make those cuboids smaller and smaller, you reduce the error, but there is a systematic bias that will not vanish with increasing resolution. Okay? And so that's actually a problem that's very actively being researched at the moment. And the key idea of trying to resolve that is to look at more complex polyhedra to approximate your continuous set. So rather than using cuboids, you use more complex polyhedra. And so the marching square algorithm is one of the algorithms that has recently been suggested. Okay, so probably have to go down here now. This image is actually 4 images in one. Okay, the top. So suppose we're in 2D and we want to estimate the circumference of a disk. Okay, which is one of the Minkowski functionals of a disk. And when you actually do the latter approach, the earlier approach that I described, what you do is you approximate your disk by a union of squares. And then you compute the boundary length of that approximation and use that as your estimate of the circumference of the circle. And obviously, if you move from a coarse resolution to a finer resolution, that estimate improves, but in the limit, you won't get rid of a systematic bias. What the algorithm does that I mentioned earlier, the Mann's algorithm, is that not only does it use squares to approximate your set, but it uses these additional polyhedra, including rotations of those polyhedra. And what you immediately can see visually, and you can confirm by experiments, is that you get a much better approximation to the circumference of the disk, and therefore a lower systematic error in your estimation. Okay, and my MSc student has extended this algorithm to 3D using these polyhedra, and then he computed the various Minkovsky functionals by computing from first principles the Minkovsky functionals of the constituent polyhedra. If you don't want to do that, so you don't want to do the computation of Minkowski functions from first principles, you can use Crofton intersection formulas, which essentially tell you that all Minkowski functionals can be expressed as integrals of the Euler-Poincaré statistic over lower dimensional sections. And if you do that, you can actually estimate the various quantities by simply counting intersections of your set with planes, lines, or points. Okay. As I said, generally this is still an active area of research, and there is no consensus yet as what the best practice is. Okay. Right. So coming finally back to the actual long example. Now, unfortunately, I have not yet got a database of long images that have been annotated by an expert in terms of the various disease states. Although my clinical colleagues tell me it's imminent that that database will be provided. So I should say that these are just preliminary results that we did on a couple of long scans, and they are not fully validated methodology. Okay. So Minkowski functionals for binary images, we talked about how to compute them. Now, how do we apply them to the long images? The long images are gray level images. So before you can actually compute a Minkowski functional for them, what you need to do is binarize the image. Then what we do is we subdivide the image into subwindows, and we compute Minkowski functionals for each subwindow. Now, so we did that, and in order to save space, my MSc student did the following. What you would have expected is for each of those slices that I'm presenting, 4 images illustrating the 4 Minkowski functionals. What he did instead is actually do a PCA and display the first 3 principal components as an RGB image. So different colors within this image characterize different weightings of your principal components. And what you see is that in areas of where you have relatively healthy lung, you get mainly greenish pixels. In areas where you have some early stage fibrosis, like here or there, you get these orangey pixels. And here where you have a slice that suffers from honeycombing, you get sort of a more purplish color. Okay. Now, one of the things I mentioned earlier was that fibrosis is characterized by light gray levels within your voxels, whereas emphysema is characterized by dark voxels. So when you're doing the threshold, you have the problem that and there is no appropriate threshold that would be convenient for every disease state. So an easy solution to that is to simply compute, to simply vary your threshold and compute Minkowski functionals for a range of thresholds. Okay. And so here is some results of doing that. This is volume, surface area, mean breadth, and Euler characteristic. Now, I must say, when I picked these regions for which I computed the functions of Minkowski functionals, I labeled them myself as being fibrotic, emphysematic, or healthy, and I was very conservative in how I would assess this. So that means that this separation between the curves is probably stronger than what I would have expected to see if an expert had actually labeled those long images. Okay, so the volume nicely illustrates the fact that you want to have different thresholds for different disease stages. And the volume is also related to what is current practice because, well, if you normalize this, then that would be 1 minus the cumulative distribution function of your attenuation levels. Okay, and so what current practice is to compute the mean of that distribution or a percentile of that distribution. Okay, but for very little extra expense, we get much more information. So as an experiment, we try to use that to do a supervised classification. Now, obviously, the data we are now having is functional data. So what we want to do is use functional data analysis to exploit the information that we have. And we used a method by Ferrati and Vieux. So as usual, we estimate posterior probabilities of the class label given our observations, and then simply classify, assign the label that has the highest posterior probability. Now, to estimate these posterior probabilities, what the method uses is a kernel density estimator. And so K is a kernel, H is the bandwidth of your kernel density estimate, which in this method is chosen such to minimize the misclassification rate, which is estimated via cross-validation from your training sample. And then by the end of this talk, I will have learned these buttons. This quantity here, D, that's just a proximity measure for functional objects. In our case, it's essentially the integral of the square difference between the new observation and the training functions. And so here are some results. And it's quite easily distinguished that the first slice is mainly healthy along with some minor fibrosis. The second slice is emphysema mainly. And the last slice is the honeycombing. But it's also nicely figured out that within the honeycombing, you've got areas of emphysema. Okay. So this is, in my opinion, a very promising approach because it incorporates what is currently clinical practice and extends it in a way that that overcomes some of the problems that I mentioned earlier with the characteristics that are used currently in clinical practice. But furthermore, it's an approach that hopefully in the future can be extended to do things like model fitting of stochastic geometry models for various disease states in lung. Okay, thank you very much.
Okay, thank you for giving me the opportunity to give this lecture here in Edinburgh. I like to come back here once in a while. Well, I want to give you a talk about image analysis and probabilistic robotics, and then give some of the aspects of statistics that are all over it, as you already mentioned before. Well, image analysis and robotics need statistics because of the inherent uncertainty in images and sensors. So in this presentation, I will give a range of examples of statistical methods that I use in my work, and which is actually image analysis in agriculture. So I hope that I can show you that image analysis really poses some interesting statistical challenges, and that you may be inspired as a statistician to work on these kind of problems. The first example I want to give is what you see here is a leaf of, for example, cucumber, which is infested by powdery mildew. And what we wanted to estimate here was the fraction of the leaf that was infested by this powdery mildew. And if you're looking at the gray values, then it's very difficult to to distinguish exactly, well, this is healthy leaf and this is not healthy leaf. So what we do here then is simply apply make a gray value histogram. What you see here, the blue line, that's the gray value histogram of the image. And then we can apply an EM algorithm fitting a mixture of two normal distributions, one for the healthy part and one for the invested part. And that gives then the red line is then the combined distribution. So now I can indeed very simply calculate the fraction of invested leaf area. So, well, this works very well if I have a gray value image. If I am using RGB images, then most of the time it gives more trouble to fitting these multivariate Gaussians with an EM algorithm. At least what I see is that when I'm looking at the 3D space, then sometimes you clearly see the clusters by eye, but you still, the EM algorithm still can't work it out. So I'm still hoping for better solutions here. High-dimensional measurements are also very common in image analysis. For example, here we have this machine which goes over the land, over grassland or whatever, and then it has a lot of several cameras in it, like a tri-band digital camera which produces images as you see here, and it has a couple of hyperspectral line sensors which produce spectroscopic data. So we get hundreds and hundreds of features, and now we have to assess something like the biomass on the grassland or the nitrogen content and things like this. And for this we use statistical methods like partial least squares and of course using nested cross-validation to estimate the number of features that you want in your least squares, and still have a reasonable unbiased estimate of for example, the dry matter content as you see here. Well, and I think that, well, you can't get around Geman and the Geman paper, as Kanti V Mardia already pointed out. This is, I think, one of the things that we are really still having a problem in image analysis. We really want to have a good segmentation, for example, and you want to get rid of so you want to integrate somehow the spectral information, the gray values, with some kind of spatial constraints, with some kind of spatial information. So Geman and Geman did this by the Gibbs sampler. Julian Bisek did it by, well, a kind of comparable but iterated conditional means. And, well, there are many, many other algorithms. And what you see here is an algorithm by a colleague of mine, which is a spatially guided fuzzy C-means algorithm, where you have this pepper image. If you just do a normal fuzzy C-means clustering, then you get an image like this, which all kind of false boundaries, as you see here. And if you do a spatial guidance, then you get rid of all these false edges. Still, the result isn't perfect, so still there is a lot to be gained here. But what is amazing actually is that this Geman and Geman paper really took off in statistics and MCMC, but in image analysis it's not used that often. It takes so much time and it doesn't produce much better results than very simple heuristic algorithms. Okay, so then I go to the part where I want to talk with you about the probabilistic robotics, or robotics in the first part. What you see here are cactus leaves that are broken in small parts, and what we want to do here is put them in the right orientation so that we can put them in a pot to multiply them. So here we just estimate the orientation of each different cactus leaf. Here you see a cucumber picking robot, which is going through the greenhouse, automatically trying to find the cucumber, then navigating an arm towards it, burning just above the cucumber, the stem, and then laying it in a box. So that's a kind of agricultural robot. And here you see the third application, which is about sorting indeed, again, cactus, but it can be anything, where they are oriented in several ways, and then we are trying to figure out what grade they are. Do they have to go back into the greenhouse, or can we just sell them already, and at what level? So these are just a few of the applications of agricultural robots that we are developing in Wageningen. And then there's one more that I wanted to show you, which is about a recent one that we are still developing, actually. This is about a rose picking robot. In the first instance, what we have to do is try to find all the roses in a box in the plot. So we are first scanning over the system, over the box. Then we have located where a rose is. Now we are moving two robot arms towards it. One robot arm is picking the rose, and the next one is moving along the stem downwards, and you can see that it tries to follow the stem here, where all kind of occlusions occur, and you really have to handle all these occlusions. And then next to the camera there's also a cutting device, so you cut off the rose, and it's picked at the top, and it's put in the basket. So we have these agricultural robots, but they are mainly based on, let's say, dedicated programming. It's tweaking, it's heuristics, and it's a narrow domain lacking an integral or a general concept. And that means that if you want to put it in another domain for another crop or things like this, you start all over again, more or less. So what we would like to do is build some kind of a better framework. But nevertheless, these applications that I just showed are really quite powerful, and they are working quite nicely. So what we want to do, what we are at the moment trying to look at, is to use a probabilistic approach in agricultural robotics. And this was inspired by the book by Sebastian Thrun, Probabilistic Robotics, where he showed that you can have all kind of uncertainties of the different devices and actuations, sensors, environment, models, algorithms, etc. And you use these uncertainties explicitly in probability theory, and then you have a generic probabilistic framework to work with. So that's what we wanted to do. Does it work? Well, it does really work, because Thrun used this approach for his car. There is this race, this competition in the US, where they first wanted to automatically navigate through the desert with a car. And the first year that they did the contest, all cars broke down within 5 or 10 miles after departure. The second time they did it, about half of the cars made it really 200 miles through the desert without breaking down and automatically navigating through the desert. And then in 2007, they said, okay, let's make it a bit more difficult, so let's go to an urban situation. So there we have, they have roads and signs and things like this, and the cars are really automatically navigating, stopping at the signboard, trying to merge in between, giving priority to other cars on the road and things like this. And this really works. He became the first, with the desert race he was the first, and with the urban challenge he was second. So this approach is really a valid approach. So we wanted to apply it in agriculture, and I want to show you two applications and show you also some of the problems that we have with it. So the first application that I want to show is also a kind of a competition, but it's much less challenging than the DARPA Grand Challenge. It's a field robot event that is organized almost every year since 2004. And here you see the teams all lined up, and with all these small robots, what we are trying to do is navigate between rows of maize in a field. And then when the maize field may be curved, and then at the end you have to detect that you're at the end, and then you have to turn around and then get into the third or second row to the left or to the right and things like this. So this is more or less the thing that you have to do. So we have this robot here participating. This is the robot, and as you can see, here's a camera at the top, and this is then the image that it sees. So it sees the line of maze here, and now it has to navigate through this lane, and then detect when it's at the end of the lane and things like this. So you have this RGB image, but that's a lot of clustering going on, so you try to cut down the amount of information that is not relevant. And if you're looking at the red, green and blue, which together compose the color image, then you can see that there is a lot of information in the different parts. And very nicely, if you're taking 2 times the green image and you subtract the red and the blue image, then you end up with this excessive green image, as we call it. And here you can quite nicely see the plants. So actually this can serve as a kind of, let's say, a probability of being a plant. So the gray value here is a kind of probability of being a plant or not a plant. So the model we made for the robot and the environment contains of 6 state variables. The state variables are as follows: that we have 2 rows in our site with a certain distance in between, an apparent distance. That doesn't have to be the real distance, but the distance as it is seen by the camera. And then, of course, with a row width. So these are the first 2 parameters in our model. Then we have a third parameter, which is actually the heading. So how is the robot oriented with respect to the parallel lines of the maze? So here it is very nicely at almost 0 degrees at the horizontal, but it can of course have a slight rotation. So that's the heading. The lateral deviation is when it's very nicely in the middle of the row or slightly deviated to the left or right. And then we have 2 more parameters stating the end of the row for both the left and right separately. Now we are using a particle filter approach to handle all the information that we have. And a particle filter is a kind of a Kalman filter, but then a non-parametric implementation of a base filter actually. The Kalman filter assumes linearity and Gaussians, and with a particle filter I can represent any kind of distribution. I can have multimodal distributions, I can have nonlinear functions in between, and all kind of these things. So that's really an advantage. So actually what it does is that I have my posterior belief I represent by a finite number of random state samples. So I take, let's say, 1,000 particles, and these 1,000 particles represent my posterior. And every particle is just a point in my posterior space. So the algorithm is that you first have some state space, some particle at the previous time step. You get some update, let's say I moved 10 centimeters, so that you take into account. And you also introduce then the noise that you have with it, all the uncertainty that you have, and then you can come up with an updated particle. So from particle at t-1, I now have a particle at time t. So then the next step is that I have all these new particles, all these updated particles, and now I have to calculate a weight for every particle. So how likely is this particle, how important is this particle in representing the posterior? And then I will do an importance resampling based on the weights of the particles. And then I repeat it every time step. So sequential Monte Carlo is a similar name. Well, this is the initialization. I'll skip on this one. Control data. We have an odometer and a gyroscope in the computer, which gives us exactly in what direction we are driving and how fast we are driving and things like this. So this gives us the way on estimating how far we were with regard to the previous time step. So then we get to this prediction step. So that means that I have my lateral deviation. I will keep it the same, but I add some noise to it. The heading, I will keep it more or less the same, and I add some noise to it. So basically everything is just adding some noise to it because of the uncertainty that I have. But for the end row, I include the displacement in the lateral in the direction. So, but then I do it in two ways. So I have one part of the particles that are really being updated in this way, and the other part of the particles that are being reset at the end of the image. And I will show you later how it works. Then I have to calculate, and this is actually the hard part, I have to calculate the particle weight. So you can very simply write this statistical formula, this formula here. So the probability of having the observations giving my current state. But this is not that simple, because my observation, my measurement is an image. So I have to somehow reconstruct an image out of my state space, and that I have to compare with the image that I have. So what we did is that we downsampled considerably to an 80 by 60 image, and that image, so from the state space vector, I make an image of 80 by 60 pixels. I draw two lines in there from the state space with the apparent width and the orientations and things like this, that I can do quite easily. And then I have, every line has a certain weight, as you can see here. So the red part is that it has a high weight. It's surrounded by a negative weight just around it, so that it tries to stick as nice as possible. And then this is 0, and then at the end of the row we add -2 to it, so that gets a penalty. So here you see the green parts are then the plants that you see in between. So now we have reconstructed more or less an image, the measurement out of my parameter. Now all I need to do is point multiply this red image with the green image, sum it all up, and this gives you the importance or the weight of this certain particle. And that I do for a couple of hundred particles, and then I'm fine. Then I normalize the particles, and I do a stratified resampling to get rid of all the particles that are really outside my true posterior, and just keeping the most important ones based on the weight. So this one has a large weight and it gets sampled 3 times, whereas this one with a small weight falls out. So basically we are using now 200 particles, 10 measurement. This still has the possibility with current computers of calculating 10 new images per second, so that's quite a fast rate. We are still using the mean state as the final decision, and it also works for navigating on the headland. And here you see a kind of the simulation. So this is the robot navigating through it. Now it reaches the end. Maybe okay. Just. So here it reaches the end of the row, and you can see here that it always slightly overestimates, of course, the end of the row, or underestimates the end of the row. But it does a quite nice job. This is more. Well, we can handle this kind of imprecision. And then when it does detect the end of the row, then it switches to a broader view, because now it has to navigate along the headland, and then it really has to see in the distance aside. And that's what you then see. It now switches to a broad view. Once it turns, here it turns, and now you see that it's still keeping track of the same lines, and now it's navigating along. So along the headland, and now it's going back into the rows again, and then it switches to the other state again, so to the small images, and then it continues driving through it. So this is the way it now works with this particle filter, and that works quite nicely. With regard to the competition, actually, it didn't work that nicely in the competition. The hardware didn't function that well the last time, so we got third for really navigating very nicely, but we didn't make enough speed. So okay, that's sorry. How much? Okay, that's good. Just before we all go to lunch, a second application that we are using, it's Rumex. Rumex is a weed in grassland. It's a terrible weed when you're an organic farmer, because then you can't spray against these kind of weeds, so you have to remove it by hand. And this, of course, if you have many hectares of land, that is a tedious job, and it can't be done actually. So you end up with all your grassland being infested with this terrible weed. Well, it's not a terrible weed, but it's not a good weed either. So they are looking for ways to automate this. This is how the Rumex looks like. Here you see the Rumex on the grassland, and you can quite easily see that this has, let's say, a high frequency compared to the leaf that you see around here. So what we are doing is that we take a Fourier transform, a local Fourier transform, or a Gabor or whatever, wavelet, something like this, which locally emphasizes the magnitude, the spatial frequency, and then this is what we are using. This is the inverse of it, as the kind of position where the weed is. And then by using a filtering, we get a very nice image where the weeds can be. Now, what we can do is that we build then a particle filter having only 3 parameters, the plant, the X and the Y, and its radius. And then we have multiple particles representing multiple locations containing the Rumex plants. And then we have to find the clusters of the particles to represent the Rumex. At the moment, it's not working with the particle filter, but it does work actually. So this device, as you see it here, is now rolling through the grassland, automatically finding all the weeds as good as possible, and that still has to be optimized. And then it puts a drill above the weed here, and it just totally smashes it to pieces, to very small pieces. So basically that's the end of my talk. I hope that I showed you that image analysis and robotics require, well, statistical methods, and that statistical methods can also be inspired by real-life applications in image analysis. And as a final thing, Chris and I are at the moment working in an EU project together, where we are looking at plants in a greenhouse, pepper plants, which are very complex plants, and we have to measure here the leaf size and the number of fruits and the stem thickness and all these kind of challenging questions. And we have range cameras and RGB cameras and infrared cameras, and we have to tackle all of this together. And that's, well, I hope that, well, having a good statistician as Chris in the group is really helpful, I hope. So, okay, this was my talk. Thank you.